So this is AstroCom. It's an advanced solar tracking and rover observation communication project for senior design here at UCF for spring of 2024. The reason we started this project is because there's an issue with exploration on the moon. There are these permanently dark locations on the South Pole that never get any sunlight, and this poses a problem for exploration because power infrastructure is limited. So we're unable to charge anything with solar panels or otherwise on the moon. And these locations are typically key areas of interest for researchers because we've never actually seen into them before. Communication is also limited in these locations because a lot of communication relies on line of sight and visibility, and because these are, again, inside of craters with high crater walls, this poses a pretty big issue.
So for specification for this project, we try to follow the goal and the weather condition of the moon as closely as possible. There are two functions, the reflectivity and the mesh network. So for reflection, we try to measure the response time and the power supply to be met so that the tower can function effectively. For the communication tower, we also want to have a constant power so that we have a constant communication network throughout the whole project. A quick explanation about the mechanism of the whole mirror towers is first we have the stepper control the W-axis with turning the whole tower left and right. Next we will have a tripod to hold up our mirror, which can be adjustable by increase and raise the mirror to a correct height. Then we can have a mirror which composed of a plexiglass cut in a round circle and covered by mylar, which have a really good reflectivity. So with this mirror, we can clearly see that it has a really high reflection using a high amount of light, and it's similar with sunlight we have been recording outside. Lastly, the rotation of the servo, as explained before, will depend on the 3D printed joint and housing.
So this is our MCU board. In the upper right hand corner we have all the regulators and the ICs for the regulators. I'm going to go ahead and power up a 12 volt power supply here and connect the board to the 12 volt. You can see both the 5 volt LED and the 3.3 volt LEDs are on, indicating that this board has both 5 volt and 3.3 volt lines active. This serves to power both the MCU and a few accessory components connected over USB-C and USB-A. We also have a strapping pin switch to select whether we want to boot or if we want to run the MCU normally. We also have a reset switch as well as a pull down switch on a separate GPIO. We also have a plethora of jumpers out for all the I/O slots, as well as some communications there. Initially, we're going to include an SD card connector, but we scrapped that idea as the SD card wasn't necessary for what we intended to do. Looking at our USB-C slots, on the right-hand side, we have the stepper switch, the servo switch, and then a laptop, connectors, rather. So this is a laptop connector there where we can boot code to the ESP as well as monitor the code that's currently running. We also have an accessory 3.3 volt regulator there, so that way we can run the 3.3 volt line from just the laptop, so that way we don't need to power the board with 12 volts every time we want to boot new code. However, I have isolated that as we don't want those regulators competing with each other. We also have the USB-A over there that'll connect to the sensor board that we'll see later, and that runs over I2C to read all the sensor values.
Okay, so this is our stepper board. This to use control the stepper underneath. For now, let me explain the stepper board itself. We will have a chip. This big chip will control the stepper and regulate the current. we have a heat sink here to dissipate the heat from the chip, because it's run on 12 volt and there's a lot of heat dissipation from these are the switch to control. For this switch in particular need to be on to divide the step of the stepper into an 18 step. All of these switch are on to control the amperage output. The amperage will be pulled by 3 amp. For now, the stepper will be connected using a power source, which is 12 volt, and running 12 volt to the board, and you can see that the power is on here, and this LED show the stepper can be run. There are two ways to connect the stepper into the MCU. First, using either pinout to connect the clock and the direction of rotation to the MCU board using output pin, or we can use a USB-C to connect directly to another USB-C at the MCU. The board also need to be connected to the stepper through 4 different terminals. This is the A terminal and the B terminal connect based on the color of the stepper, color coding of the stepper. We use a joint connectors and a slip ring to prevent the tangling when we try to rotate the tower. With the tower, we have a big plate, and the plate will be rotated using a gear mechanism. And underneath the plate, there are support to use a bowl roller to support the weight of the whole tower to prevent any bending. And underneath the tower is the stepper, which connect through the slip ring. And this is the stepper and the stepper housing. That pretty much it about the stepper. The stepper and the MCU can be put into its housing using a groove. This is housing for stepper, and this is housing for the MCU. The stepper will be running on a 12 volt and approximately 3 amperage. So this is our servo board. It will use to be controlled 3 different servo, X, Y, and Z. The first servo will control the movement of the sensor housing. The second servo will control the x-axis of the mirror. The last servo will control the y-axis of the mirror. Through these 3 servo will run through a mux using I2C, which connect to the to the MCU's board, which this regulator right here will take in the 5 volt input and will regulate to 3.3 and control the mux. We also have a connector using USB-C to connect to MCUs, which will run to use the I2C. Right now, the regulator is connected externally to a 5 volt source, which can be seen by the LED that this board is turned on.
So this is our sensor board, and the sensor board has 5 different VEML 7700 sensors that work with the sensor multiplexer. And how this works is it comes through the I2C data line through this USB-A cable, and it will be able to read from each sensor individually as it goes through its reading values and reading functions. And these values will be tested against each other to determine to move this motor vertically or also move the stepper horizontally. And this works because it has the partition, which gives it dividers so that light can't hit all 4 sensors at the same time if it is off. But once it is directly on the source, it should theoretically have all of the light values be the same.
All right, so this is the charge controller we're using. This is going to take the DC from the solar panel here, which is typically going to be about 24 volts. We're inside, so I got that simulated with a 24 volt power supply. I'm not sure if the figure comes in there.
That's good.
All right, but this is going to charge the battery and also allow any subsystems to run off the 24 volt from the solar panel, but it is going to step it down to 12 volt. Right now I'm connecting our lithium iron phosphate battery. It's typically 12 volt. I'm going to plug that in, and then we can see the current on our power supply just increased because our battery was drained. So it's now charging our battery there off of what typically would be the solar panel. Today we're simulating it with the power supply. I also have a multimeter here, just to confirm that it is indeed outputting 12 volts for all our subsystems. Sorry, I got my probes a little mixed up here. There it is. About 12.6 volts, which work just fine.
All right, so this is the communication tower part of the project. So in the final version of the project, this coordinator dongle here will be running on the rover, but for demonstration purposes, we are showing it with hosting the coordinator through this Raspberry Pi over here with this dongle. If you look inside of the comm tower box here, we are running a battery that's powering this microcontroller, and this microcontroller is working as an end Zigbee device. So when I push this button, it can send a signal that will tell the tower to do something. In our original software design in the paper, it was said that this box would function as a intermediary device that could extend communications. It can still work that way if we use router firmware in here instead. But currently this is the best way to show we can send messages using wireless and control our devices. So to demonstrate this working, I'll run npm start here, and that's going to be able to show the MQTT console, which is the messaging protocol that we're using here that communicates with the Zigbee from the native and Zigbee device. All right, so now once it's starting, you can see that we have published this message saying that our device is called Flashbang. So this tells it that this Flashbang here, he is on the network. We can also verify this by going to the front end here. So here is Flashbang. He's here. The connection is perfect, and it's working as an end device. So once you actually go in here and push this button, you can see the message comes up. It receives the Zigbee message from Flashbang, and when the entire system is online, this controls our tower movement, and this message can also be seen from the rover's mobile app. So it's the comm tower demonstration.
So here we have our tower doing the initialization. So it should be identifying the first target, which is right there, I believe.
Yeah.
And then the second target is right there, as the mirror is currently pointing at those. Once we update the sensor, it should begin tracking target 1 and reflecting light there. So you can see it snap back to the first target, and the reflectivity is working there. So you see both things are adjusting to the new sun's location. Let's see how accurate. Okay. See, that's live tracking, and then we also have the Zigbee element where the outside tower can update the target over communications. So once Pedro presses that, it should snap to the new target. After an update here.
Press it. Now I just did. Okay. Once the stepper starts moving, there's the switch of target.
There we go. So it just switch targets there.
It's just like kind of towards the lab safety.
It'll live track that one now. You see, both things are adjusting for that new input.
Some challenges that we are facing at this moment, since we choosing switching to new board, is because the distance from this housing at the bottom to the housing to the other board of the sensor board and the servo board, there's a long distance. So when we implement a USB-C cable to connect between the two, because of the length of the wire is too long, it increased the capacitance. To combat this situation, we try to implement a repeater to repeat the data so that we can read sensor value from the sensors, and we can just connect directly using a long USB-C cable. Another challenge is the switching between the stepper board. This is a dead board. which work well with the stepper before in previous testing with a particular stepper board due to the reduce in voltages, and there's some problem, the stepper not hold enough amperage, which we are working on to fixing, and hope and we will be able to finish in about a week.